Next talk will be by Hao Xu from the DICE Center on Pluggable Rule Engine Architecture.
Well, I can try. All right, let me just start. My name is Hao Xu. So, oh, sorry. Let me get started. After I put this microphone on. Okay, so my name is Hao Xu. I'm from the DICE Center, which is a data-intensive cyber environment center, and I'm the main designer and implementer of the iRODS rule engine since iRODS version 3.0. And I'm also the main designer and implementer of this pluggable rule engine architecture that I'm going to talk about today. But I want to also mention my colleagues, because this thing is not a project, sort of like isolated project. It is something that is closely interconnected with other parts of iRODS. So their work, Jason's pluggable architecture and dynamic PEP, and Ben also volunteered to be the first person other than me who writes a rule engine plugin. So they both contributed significantly to the topics that I'm going to cover today. So let me go to the introduction. So first of all, let me ask you this question. What is a pluggable architecture? Like, what does it mean? Like, what is the essence of pluggable, and why do we need a pluggable architecture? Okay, so here's a simple illustration. So supposedly you have one piece of monolithic software which implements certain features, right? So, but someone came in and asked you, oh, I have a new feature that I want you to add to your software. Can you do it? Right? So if you only have one piece of software, how can you do it? You have to modify the source code. You have to recompile everything. So basically, you have to do it as a whole. You can't, like, say, I modify this part and I just do my change on this part, and without having to worry about the rest of the stuff. You can't do it with a monolithic piece of software. So what you want to do is you want to divide the software into two pieces. You call one piece the red piece here, the core, and you call the blue piece here, the plugin. So what does this give you? What does this division give you? It gives you the benefit of simplicity and flexibility. It's simple because now you can, when you want to implement a new feature, you keep the red part, the core, fixed. You just vary the blue part. So it reduces the amount of work you have to do when you implement a new feature. It's flexible. For example, you can say, oh, I can vary the blue part and create a new feature, right? So, and it's also flexible because you can vary the blue part in different ways, and that gives you different features, like this. So then what is the most challenging problem in this sort of a task is creating a pluggable architecture, specifically for this pluggable rule engine architecture. The challenge is really where to draw the line between the red part and the blue part. So I'm going to show you two cases what not to do when you create a pluggable architecture. So first case is if you draw it too far to the left, it's not simple anymore. You're basically creating a new piece of software whenever you create a new plugin. There's very little code you can reuse. The second what not to do is if you draw the line too close to the right, it's not flexible, right? There's not much you can change, not much you can vary. There are too much constraints you put in your pluggable architecture that you cannot implement the features that you want to implement. Okay, so with that introduction, let me just come back to the rule engine pluggable architecture. Okay, so over the years we have collected all these requirements from our users. They're very different requirements, and they seem to require different kinds of solutions for each requirement. But hopefully after this talk, I'll convince you that the rule engine pluggable architecture provides a general solution that satisfies all these requirements. So in addition, I set these goals when I designed the pluggable architecture. First of all, the simplicity. I want to allow the users to create new rule engine plugins. And by the user, I mean the users who are not me, like other people. To be able to create new rule engine plugins by writing only 100 lines of C++ code. So if they want to implement a plugin that allows you to run Python microservices, for example, they should only have to write 100 lines of C++ code to create that plugin. And after they create that plugin, they can distribute that plugin. Then whoever installed the plugin on their computer should be able to run Python. So that's the simplicity. Okay, so also I want to be flexible. Run multiple rule engines concurrently, fully backward compatible, which means you can run the Python plugin, you can run the iRODS rule language rule engine as a plugin. You can even run domain-specific rule sets as plugins. And they can all run concurrently on your system. So this way we will ensure full compatibility as long as you include the iRODS rule language plugin in your system. All your rules written before 4.3, they all work. So also interoperability with other programming languages, Python, C++, JavaScript. Let me just ask you this question. Supposedly, let's take iRODS out of the context, and I may ask you this question. Suppose you have a program written in Python, and you want to call a function written in JavaScript. Can you do it today? Can you do it today by writing only one line of Python code and nothing else? Can you do that? So with that in mind, let me show you what we have done. Okay, so what I'm going to talk about today is two basic points. The first point is pluggable rule engine architecture, which is the general kind of a solution, the abstraction, the architecture. So basically, I defined a new type of plugin called the rule engine plugin, and I defined a set of plugin operations. Actually, there are only 4 plugin operations you have to implement when you implement a rule engine plugin. And also, I'll show you 5 rule engine plugins we have created so far. And so the second topic is generalized policy enforcement points. This is a very specific application of the rule engine architecture. And I'll show you the flexibility and how we use the generalized policy PEP to solve some of the problems that I listed in the introduction slides. So in general, this is a one-slide summary. So I wanted to really go into a lot of technical details when I prepared these slides, but then I realized, okay, so there's not much enough time to do that. But if anyone wants to know the details, I'd be glad to talk with you after this presentation. Okay, so generally one-slide summary it's actually very simple. Conceptually, it's very simple. There's the iRODS core, then this is the rule engine plugin architecture. It sits between the iRODS core and the rule engine plugins. So basically, you can attach any number of rule engine plugins to the plugin architecture, and they will run concurrently. Okay, So that's the big picture, right? So it's very simple. So and the second block here says all you need to know to implement rule engine plugin. Only thing you need to know is you need to implement these 4 very simple functions: start, stop, rule exists, that tells the iRODS core whether a rule exists or not, and exits rule. So basically, the iRODS core says exits rule, then it exits the rule. So that's very simple, right? So then there's one thing is how do you like within your plugin? What if you want some information from the iRODS core, right? How do you do that? So there's actually a callback object, so which is passed into the rule engine plugin, and the rule engine plugin can use this callback object to go back to the iRODS core. So this is the only point of entry from the rule engine plugin to the iRODS system. Why this is important? So we'll see in the second part of the show. Talk. So rules defined, and also rules defined. This way, rules defined by one rule engine can call rules defined by another rule engine. So basically, if you have a rule engine plugin that implements Python and another implements the iRODS rule language, they can talk to each other through this callback object. Okay, so applications. So as I said before, we have 5 rule engine plugins. So there's the libRE, that's the mystery rule engine plugin, which will be unveiled in the second part. And libaudit, the name suggests it's for auditing. It's also second part. But let's focus on the 3 rule engine plugins we have now, the general purpose rule engine plugins. The first one, librE iRODS, that's the iRODS rule engine plugin. So basically, the iRODS rule engine converted to a plugin. Then there's librE Python. So that's a proof of concept Python rule engine plugin, which allows you to run microservices written in Python. So Ben standing next to me here, he volunteered to create this one. So very brave. So then after the Python rule engine plugin, I was thinking, okay. So remember I said it's all about where you draw the line between the core and the plugin, right? So we've achieved the goal that the essential code of this Python rule engine plugin is only 100 lines of C++ code. So, but you might ask the question, okay, maybe it's because you designed the rule engine architecture in a way that it makes Python, it sort of caters to the needs of Python. It makes writing this Python rule engine plugin especially easy, right, compared to writing a rule engine plugin for other languages, right? So I really want to, I don't know, maybe it's by accident, it's definitely not by purpose, right? So I really want to be able to sort of validate this idea of you can create a rule engine plugin for any language with a reasonable foreign function interface within around 100 lines of code. So I create this JavaScript plugin. This JavaScript plugin is based on Chrome's V8 JavaScript engine, and it turns out to be what? Roughly 100 lines of code, a little bit over, but roughly 100 lines of code. So that sort of validates the simplicity and flexibility. Simplicity, 100 lines of code. Flexibility, you now have JavaScript. You can write some microservice in JavaScript. You can write microservice in Python. And you can write microservice in any language that you can think of as long as you write 100 lines of C++ code. OK, so now let's get to the demo. So here's a very simple example. User, OK, so the top part is the good old iRODS rule language. So here, you as people who are familiar may recognize, you can do AC post proc for put. That's a policy enforcement point. And you can do a bunch of stuff. Usually in the production system, you want to delay this rule. And then you also want to remote this rule so you can run your computation at the resource which has the sort of computational power. So it can be done using this. It's very easy to do this in the rule language because the rule language is designed for distributed system, like iRODS. So you can say delay. Well, you delay 0 seconds, which basically means you want to do it asynchronously. You don't want to do it synchronously. So you can return from this rule as soon as possible. As soon as this delay execution is submitted. So the remote says, okay, you go to the remote resource called the computing resource. That's the name of your server that has the computational power to do the computation. And then you say, I want to call this Python function on this object to actually do the computing. That's all you need to do on the rule language part. On the Python part, it cannot be simpler. You just define this Python function, and you do whatever you want to do. So you see this object path is mapped to here, and this iRODS is the callback object. Let's say if you want to write the log back to iRODS using the writeLine microservice, all you need to do is this one line. You say iRODS.writeLine, the same, whatever you want to write. Okay. So let me see some real code. So here I have a bunch of rules that I created before this beforehand. Let's see. Okay. So let's see. Let's look at the simple ones first. So Python. Okay, so this one is a little bit different from what because I want to show something even more in this demo. So I define the Python function first. I write a line log. I write to the server log the parameter a, and then I append space Python to the parameter a. Then I go to the callback function. I says, okay, now I want to call a JavaScript function defined this way. So I say iRODS.js func. And I pass the parameter to the JS func. Now remember, now I have a concatenated Python to the parameter. So okay, so let's go to the JavaScript one part. Okay, so very similar, right? Except the syntax now is JavaScript syntax. I define the function, and it says writeLine. I write server log, and then concatenate JavaScript. Now I call a iRODS function written in the iRODS rule language through the callback. Right, so basically I go from iRODS to Python to JavaScript and back to iRODS, and along the way I call microservice every time I call a new function. I call the writeLine microservice to write to the log. Okay, so let's search for the final part of the final piece of the puzzle. So here I define the iRODS rule which initialize the parameter as with iRODS, and I call the Python function, and the second rule there, iRODS func, which is basically I just write whatever it receives to the log. So eventually everything goes as expected. What should I see? I should see logs along the way, and I should see the completed string that contains iRODS, Python, and the JS. Right. So that's what we expect. Okay. Let's see whether it does that. So I run this iRODS rule through using the iRule command, and I come here to the log. What do we have? We have iRODS here, iRODS Python. Sorry, the line is kind of breaking into two parts. But here, iRODS Python JS. So everything works full interoperability, zero syntax overhead. And you can create a rule engine plugin for your favorite programming language using by writing only 100 lines of C++ code. So this what are the applications? So let's say you have a Python script somebody gave you, like do certain analysis, use NumPy, those libraries which are previously not available for iRODS. Now you can call the Python script just by the function name of the script. Right, so you don't need anything to do here. So that sort of that sort of concludes the first part of the talk. Let me move on to the second part, generalized policy enforcement point. Okay, so this part. Okay, so before I go into details, let me just mention there's a long line of research and development in policy enforcement point, and is definitely one of the most distinct features of iRODS, and which gives the iRODS a lot of power and customizability. So it was originally developed. The concept was originally developed by the DICE group, and here's one of the many papers they published before I joined the group in 2010. So the paper was published right before I joined the group. So this is. So basically, this first paper described the concept of policy-based data management, which includes the policy enforcement point. And then Jason, for iRODS 4.0, he created this dynamic PEP, which basically says, OK, I take this concept and generalize it to all plugin operations. Now, every plugin operation is equipped with pre and post two policy enforcement points. And then I sort of published this paper, which kind of formalized the idea of policy enforcement point into this very simple one-line mathematical sort of notation, which is basically saying, OK, consider F to be to denote the sort of the iRODS core. OK, F is iRODS, right? So you have a request coming in that says operation arguments environment. And what iRODS does is before you do this operation, it generates a pre-rule call and post-rule call. These are like rule calls. They're not the actual rule. You have defined actual rule. So you generate pre-rule call and the post-rule call, and you can sort of do a lot of stuff here. Like you can have like post like AC post proc for put, right? So the operation is put, and then this post op is AC post proc for put, right? So that's a concrete example. Or you have AC pre proc for file open, that kind of thing. So then operation is file open, and this pre op is AC pre proc for file open, right? So there's or file create. One of them is present. Okay. So the idea is really the dynamic PEP is kind of like, okay, so now you have operation, then you have a plugin architecture sitting sort of in between your iRODS core and your plugin, right? So now the responsibility of generating pre and post in dynamic PEP is sort of done in this plugin architecture, but the basic concept is very similar. So this form is very useful. It's been adopted to wide range applications, as we've seen demonstrated by the numerous talks yesterday and today. However, there's one tiny problem, right? So the semantics of F must be fixed in the iRODS implementation. So what I mean is it means this equation here is fixed. This formula is fixed because it's part of the plugin architecture rather than being part of the plugin, right? So the conundrum for iRODS dev then becomes the core devs becomes, okay, so how do we design this F to fit as many use cases as possible, right? Should we make op to be skipped if pre-op fails, or should we still call post-op if pre-op fails, right? So iRODS has a strong tradition of ensuring that a lot of semantics are configurable, so we want to be able to provide configurability plus strong default. So after many years of designing and tweaking, I think the current state is we have a very strong default. So the F that is currently implemented in iRODS have a wide range of applications, but I want to add this configurability to it. So the key here is to be able to write policies for policy enforcement point. For policy enforcement. So before you write policies for data operations, now you want to go one level up. Say, I want to write policies for policy enforcement. Okay, so how do we do that? We generalize this PEP, generalize this equation. Often when you find this is very interesting things, is when you generalize something, it becomes simpler. So this is what happens is, you generalize the F to F generalized. So now you don't even do the post pre-post. What you do is you just say, I call a higher order function. It's higher order because OP here itself is a function, right? I call a higher order function, and I just simply supply these three parameters to it. And now PEP becomes a policy that you can implement in your rule engine plugin. For example, this is a very simple implementation. This is pseudocode. This is not real rule engine code. Okay, pseudocode says, we can say PEP, OP, args, ENV. So what does this says? It says, okay, I don't care if pre fails. I just do the op, right? You pay pre can fail or not. I don't care, right? The simplest semantics, right? So or I can say I really care about it, right? If pre fails, I don't even want to run the post op. right? This one you can implement as a separate rule engine plugin or as a separate rule. So when you place this rule in your system, it implements this semantics. So you can always also say, okay, if pre fails, I don't run the up, but I still want to run the post up. Okay, 3 possibilities. Okay. So to put it in a picture, what we have here is now the rule engines form a hierarchy. So when the plugin actually calls this PEP, there's a sort of a meta rule engine which implements the PEP rule and interpret and sort of create these pre and post and do all the delegation and stuff, right? So that's sort of not really delegation, but like sort of a dispatch, right? So that's sort of so now you may say, okay, good, you create this really fancy stuff that just give me this different variation of error handling, right? What else can you do, right? What else can this architecture do? So in fact, you see, I can create multiple pre and post. Like I can have 2 pre rules and 2 post rules. Like what is the application of that? Here what you can do is you can put those pre rules and post rules into different namespaces. So by default, I have this empty namespace, which is just the pre and post rule you have today. But I can create a different namespaces audit and different namespaces set index. So what you have is something like this. It says audit PEP something, audit PEP something. So basically, when your rule lives in a separate namespace, it creates a modularity in your system, which means you can distribute these policies without affecting other policies. So for example, now if I want to add auditing, before it was very, very kind of tricky to do it because you have this one AC post proper put. You may be doing some delay execution there, right? If you want to add auditing, you have to modify that rule, and you have to ensure that auditing happens in the right order. It doesn't interfere with the delay execution, all that kind of stuff. It kind of requires a much deeper understanding of the rule language in order to do it correctly. So now what you can do it simple. There's an Audit plugin which provides this capability. The Audit plugin is an example of a fixed semantics plugin, which means it's a rule engine plugin, but it encapsulates a fixed set of rules. The user cannot change the rules. The user can use the rules. So this is what I've said in the beginning is sort of the modular distribution of policy. Now you create a set of policy before you have to give them the rule file, right? They have to manually incorporate the rule file into their core RE. But now you can just give them a policy, and they give them a rule engine plugin that contains your policy, and they can implement, use this plugin just like they use any other plugin. So its Audit plugin it runs a native speed because it's actually written in C++. So that is important because you don't want too much overhead to your system when you enable auditing. So you don't want to interpret the language, you want to compile the language. It supports any future plugin automatically. So which means if, say, Jason created a new type of plugins in the future, this auditing plugin, you can keep using it. You don't have to upgrade. So it can move at its own pace. This plugin can move at its own pace. So when you upgrade your system, as long as the rule engine plugin interface hasn't changed, as long as the fundamental architecture of iRODS hasn't changed, which is unlikely, well, I can't say that, but at least foreseeable future, right? For everything I know, you can keep using this plugin without any change to your code. Okay, so this plugin, what it does is listen to the audit namespace. So here's an illustration, sort of like a pseudocode or like in the rule language, but in the actual implementation was in C++. So basically, this is like boils down to this. So you have this pre and post, and you write a server log containing all the information about this operation, right? So that's what you need. Okay, so this is all you need to do to enable this plugin. So first of all, you say, oh, I create an instance. In your server config.json, this is not rule language or C++ or any program language. It's just a very simple JSON, right? So you say instance name, RE audit instance. Instance name, RE audit instance. Yeah, that's correct. Plugin name, RE audit. Namespace, you enable this namespace, and you enable the plugin. That's all you need. All you need to do. Okay, let's see a demo. Okay, so here, let me just enable this namespace. I already added what I did is I have this X put in front of it, so it's sort of create a different namespace that sort of detracted from not going there. So now I restore the name. Restore the namespace, and you see I've already have the plugin here. Okay, so let me just do an iOS. Go to the log. What do we see? We see auditing generated in a JSON format, right? So here you can say, okay, some agent is started. Who started the agent? iRODS, temp zone, privilege, and you can see all kinds of other operations here too. You can see this agent start. Then you can see database operations, and you can see jQuery. We can actually do, since I still have time, we can actually do one more thing. Let's do input. Let's put the core RE into the. Sorry. Yeah. So this is because I need to. This is because I was using the old. .iRODS env file, which doesn't have the number of threads when I do the parallel put. So that's what it says. Okay, let me just check. Yes, I have now I have the new one. So so in this iRODS account, so let me just say plugin RE lib RE v8. Okay. So I put this v8. Okay. So now let's see what kind of logging it generated. General auditing. See, so you see it says audit pre-rule exit rule. I audit PP rule exit post AC post powerful put. Now you can audit not only all the plugin operations, but every rules and microservices that's ever run on your system. So you can make sure that everything that changes your system, you have a log to show that. So I think this is something that's really important for some applications. And also I'm trying to find the file put operation, the actual operation, the log of the actual operation that. So here it is. Okay, audit stat. So here you are doing stat operation. This is like sort of what's happening. This is your resource hierarchy where it happens, and this is the logical path where it happens. This is what the user, like the user credentials, and that's stat and register. And this is resource write. You see, where there's a resource hierarchy, file descriptor. I think this is the length, or so logical name. So by the way, all of these stuff, this information are made available by Jason's work on the plugin architecture. So basically, he generated this huge key value pairs, which is passed to the rule engine. So I can use them to I can do them to display here. So something more interesting. Okay, should I take questions or? We have time. Okay. Let's try something interesting. Okay, so iRODS, they have this arrow. Let's see. Am I at the right place? Okay. Yeah. Okay. iRODS does this kind of error handling, right? So let's see. So if I say throw demo at UGM. Let's see. So if I say okay, I throw an exception here. Okay. So what will happen if I try to call the rule? Now, what will happen? Am I doing the right thing? Okay. Right. I forgot to disable the audit, so it's kind of overloaded by the okay. So here it's logged on at the in the log. So you can throw exceptions from within your JavaScript or Python or anything. It's fully integrated. So and also you can also say if I say okay, if I say here says okay, I try to call something that's non-existent, for example iRODS.a. Let's see. So let's see what happens. Here is if you say here. Sorry. Here. So you can actually try and catch the error here. Okay. Let's see. See, so the iRODS error code is made available to the JavaScript code. So this way you achieve full interoperability. Not only when you are successful, the rules are successful, but also when there's an error in your rule or in the JavaScript rule. So yeah, I'll take. I guess I'll refrain from keep mission creeping, and I'll just take questions. So notice the one thing before I take question is this is pretty much work in progress. So if you this is actually not in the iRODS 4.1. It's as far as I know, it's going to be in the next release. And so what happened here is what I'm showing here is there's a repo which basically like my personal workspace. Which I have the code GitHub repo on there, and what we'll do is we'll do a pull request and we'll merge it to the main repo. And the other thing is so these rule engine there's a limitation. I have to make this disclaimer because we currently only in this demo we only handle strings. But it's very, very easy to handle other data structure. It's just like the time was so limited before this. We didn't. But like we said before, this is sort of like the same thing as a pluggable architecture, right? The data type handling is actually sort of like also like itself is like a plugin within plugin. So we can actually do that for other data types very easily. So if you find the code on the internet and you run, if you say I try the integer and it doesn't work. Here, I told you here. So because you currently only handle strings. Okay, questions?
I just want to point out that this is being answered to my prayers. Is this a branch of 4.1?
This is actually the way maybe Taro can explain to you more is iRODS has this policy of not creating branches. Because it'll be very difficult to be managed by a small team. Because this is a pretty huge feature, so they suggested I fork and I do the development, then I send a pull request and then merge. So this is actually at my personal namespace iRODS / GitHub /xu. Well, I can give the URL. Yeah. Yeah, there's a separate branches. There's separate repo, one for this and one for the plugins, like one for the architect, one for yeah.
It's effectively a branch.
Yeah.
I'm just thinking logically, it's a branch of 4.1. So if I
right.
put it in right now, I'm loading 4.1.
Yep.
So I place modules in the Python on the iRODS or the ICAT server, but I can import them into those plugins.
You have a Python module. I'm sure now. I'm not sure if I understand your question. Like what is?
I think I know the answer to this one.
Okay, go ahead.
The way that the Python plugin works right now is that it sources all the function calls to etc iRODS core.py, and as far as Python developers are concerned, etc iRODS core.py is a Python source file, and you can do whatever you want in it. So you could, if you put another, and we append the import path etc iRODS to the Python interpreter. So you put any Python file you want in etc iRODS, and you can import it directly from core.py. Yes.
Okay, so basically, that's the only interface between you and Python. So if I understand correctly, you can put any Python module you install on your system, and as long as those modules are available to Python, they're available to this. Does that answer your question? Okay. Okay, thank you.